You are in an interview and the interviewer hits you with a tricky question. What is the bias and variance trade-off? You have just a few seconds to impress them with a clear and confident answer. Don't worry, by the end of this video, you will understand these concepts and know how to explain this in the way even the school grade can understand. Imagine you are playing a game of darts. When you throw a dart, they landed on a board. If all of your dots landed far from the bull's eye but closer to each other, then it's like a high bias. Your aim is off, but you are consistent. If your dots all over the places, some closer to bullseye and some are far, then it is a high variance. Your aim is on the target, but it is inconsistent. In machine learning, bias is an error from the model that is too simple, while variance is a error that is the model is too complex. Now, here is where it gets tricky. The bias-variance trade-off. If you reduce the bias to make the model more accurate, you might increase the variance, making it less reliable on the new data. If you reduce the variance, your models might be too simple and miss the important patterns. The goal is to find the balance where both bias and variance are low. So, your model performs well on all the data, not just the training data. Think of it like a balancing a seesaw. Getting just right, and your model will perform like a pro. Let's take a simple example, predicting the student score. If you are only considering the number of hours studied, you might miss out some of the important factors like sleep or previous knowledge. This is the high bias. But if you consider too many factors like what they had for the breakfast, your model might become too specific to the students in your classes. This is a high variance. The challenge is to build the model that is just right, considering enough factors to make accurate prediction without overfitting. How do you balance these factors? Comment below with your thoughts. Let's jump into some code to see how this works in a real life. Well, we will start with the simple linear regression model. Then we will move to the complex polynomial regression. Finally, we will use the cross-validation to find the balance between bias and variance. Alright, let's write a code for comparison. It might look a bit complex at the first, but don't worry, I will break it down by step. So first thing first, we import all the libraries we needed. Well, we have a NumPy for generating some synthetic data and Matplot for plotting and few functions from the scikit-learn, which is a powerful machine learning library in Python. Let's check out. For NumPy, let's see. Import Matplotlib is not my plot. Scaling selection port test split comma validation scope scale dot linear model for linear regression scale dot preprocessing preprocessing for polynomial feature from scalar dot Python import make. Okay, so we start with generating some. So we have imported all the libraries. Let's execute. Okay, so we start by generating some synthetic data. What does that mean? Well, instead of using the real world data, we are creating our own data from testing. Let's check it out. speed of 42. My x is equal to number dot sort then dot random dot then 100 comma 1 into 10 is equal to 0. Y is equal to np dot sine of x dot zero comma 0.1 comma start ship. We are using np.randomSeed42 to ensure that we are getting the same random numbers every time we run the code. This helps to keep the results consistent. Here x is our input data, which is a series of 100 random numbers between 0 to 10. We are using np.sort to sort the numbers. The y is our output, which generates using the sine function with some added noise. The noise is added using np.normal, which gives our data more realistic and scattered look. Next, we split our data into training and testing sets using train test split. This is an important step in machine learning. Let's check it out. Split the data x underscore train comma x underscore test comma y underscore train comma y underscore test is equal to trains test split x comma y comma test size is equal to 0.2 comma random state is equal to 42. We train our model on the training data and then we testing its performance on the testing data. Here we are using 80% data for the training and 20% for testing. Now we move on to the linear regression model. Linear regression model is one of the simplest type of regression in machine learning. It's try to fit the straight line through the data points. We create our model using linear regression function and fit it on the training data using the model.fit. Let's check out. Linear regression. We create the variable model linear regression model dot x underscore prime y underscore train. Then we'll print the linear regression CV score. So print. Next we will print the linear regression CV score. So print linear regression CV score cross validation score of model comma yes train y train comma CV is equal to 5 dot me so we got this CV score cross validation score. After fitting, we use the cross-validation to check how well our model is performing. Cross-validation splits the training data into similar parts and trains the model multiple times to get an average performance score. This helps to getting a more reliable estimation of how well the model will perform in the new data. In our case, linear regression CV score is printed, which gives an idea of how well the model fits on our data. Polynomial regression can fit the curve in our data. This makes it more flexible and better suited for data that isn't linear. Let's check out. As we come to is equal to pipeline polynomial feature degree linear regression model fit x underscore train y train print polynomial regression print polynomial regression score make small change here function degree will print here. Degree is equal to okay, then see the cross-validation score is cross-validation score x underscore prime number so is equal to 5. Okay, let's execute. Yep. We use polynomial features and to add the polynomial terms to our model. Here we set the degree to 4, means it can fit a curve with up to 4 bits. Then we use the make underscore pipeline to create the pipeline that first transform our data with this polynomial feature and then apply the linear regression on top of that. Just like that, with the linear regression, we use our cross-validation to check the performance and as you all see, the CV score of the polynomial regression is used to much higher, especially when the data is non-linear. In linear regression, it is a negative, and when in the polynomial regression, it is a positive, which is a much higher. Now finally, we will plot the results to visualize the comparison of the model. We are using matplotlib to scatter a plot that original data points in black and then we plot the predictions on both the models. Let's check it out. Plotting. black. Dot edit of x, comma color is equal to blue, level is equal to linear regression. Mod dot only dot predict color red, well, something else. Okay. Plot dot show. Okay, what's there? Okay, something x y score data color, I guess. Okay, the blue line represents the linear regression and the red line represent the polynomial regression. Notice how blue line, which is a straight line, doesn't fit the data very well. On the other hand, the red line bends and curves to the fit the data much more closer. On the other hand, red line bends and the curves to fit the data the much more closely. This clearly shows the advantage of using polynomial regression for this type of data. So the linear regression is simple but not always capture the complexity in our data. Polynomial regression, on the other hand, is more flexible and can give you better fit when they're dealing with curves or non-linear data. As you can see, the simple linear model has the high bias, missing the curve in the data. The polynomial model fits the curve better but might be overfitting. Using the cross-validation help us to find the sweet spot where the model performs best on the new data. Pause this video and try to change the polynomial degree, and what happens, let me know in the comments below. When you are in the interview, here is you can explain the bias-variance trade-off clearly. Start by giving the simple analogy like dot example, then explain how in machine learning. Bias is about how well your model matches the true data, while variance is about how much your model predictions vary with different data. Finally, mention how you can use these techniques like cross-validation and regularization to balance them. After explaining, you can impress the interviewer by showing the code example. Explain how you use the cross-validation or regularization in the past project to manage the bias-variance trade-off and improve your model performance. What's your go-to explanation for the bias-variance trade-off? Let me know in the comments. It can be helpful for other students also. To sum it up, the bias-variance trade-off is all about finding the right balance in your model. You want to avoid the being too simple or too complex. By understanding this concept and practicing it, you will not only build a better model but also ace your interview. Mastering the bias-variance trade-off can be difference between the good model and the great one. If you found this video helpful, hit the like button and subscribe and share it with your friends who are preparing for the interview. And don't forget to comment on which topic do you want to use to cover next. Until next time, keep learning, keep coding. Bye bye.